Hello, people. We have thus far walked through some solutions of vector addition problems in a couple of with a couple of methods. Um, One of those was by doing some pretty careful tip-to-tail addition, and I mean pretty careful with use of ruler and protractor. And we talked about some component solutions. And we actually did those with rulers and protractors, but I kept saying that typically, while the style of the component solution, we were doing the right style, we were doing them in a way that we wouldn't typically. Typically, we will never measure with a ruler a component. We'll calculate the size of the component. So we get to a place where now we can solve questions like this without using rulers or protractors at all, which might be more convenient. So let's make some assumptions. Here's two objects that are going to interact. They're going to stick together. So says our statement of the problem. And let's just define some quantities. Let's say that M1 is, I don't know, how about 40 kilograms, some would say. And how about number 2 here is, let's make that 60 kilograms. And V1 initial, let's make that, how about 8 meters per second. V2 initial, let's make that 7 meters per second. And this angle, theta 2, that looks like, what do you think, like 65 degrees? Sure. Okay, now the component solution means that what we're going to do is we're going to find, well, now this says we're going to find the velocity of something, but to do that we're going to have to know the momentum first, and just use momentum as m times v. So we need to find P system final by finding P sys final x and P sys final y. If we know the components of the final momentum, then finding the total final momentum isn't too bad of an operation. So how do we find these components of the final answer? Well, to do that, we use what's called a component solution. So to find P system final x, here's what we do. We say the initial, oops, I already screwed up. We say the initial x momentum must be equal to the final x momentum. So says conservation of momentum. All right. Now, how do we do that? Well, even if you're not provided with a drawing, you might only be provided with, say, this information in some nicer narrative sort of description. What you really should do, what I really recommend, is making a sketch of these vectors. All right, so not with a ruler and protractor, not to scale, just making a sketch. And so when you have this sketch, what you can do is quite literally say, all right, well, here's a component, right? This is, well, let's just call this one P1 initial. It is. Let's call this one P2 initial. Here's P2 initial y, and here is P2 initial x. So drawing those components, just sketching them, goes a long way towards your ability to do this correctly, to write that expression for net momentum. So again, let's look at our diagram. All the initial x momentums. Well, there's P1 initial. And we don't even have to say x, because the whole thing is, points in the x direction. And then we've got P2 initial x pointing in the opposite direction. Well, that means we've got to be clear about the sign convention we're using. I'm going to use a standard convention where up is the positive y direction, right is the positive x direction. So this says, well, explicitly, P1 initial is, quote, in the positive x direction. P2 initial x component is in the negative x direction. Well, that gives us the sum of all the final x momentums. I'm just going to call that P system final x. And I'm calling it P system final x because these things stick together and move as a system. Okay? Now, how do how do we find these components? Well, I mean, let's see. P1 initial is M1 V1 initial. Yeah? Now, P2 initial X, I'm going to do a couple of steps here. This X component of P2 initial is adjacent to that theta 2. Right? So I can write it like this. P2 initial cosine 65. How about theta 2? If that eludes you, then I will refer you to a previous set of slides where we said something like this. Here's a momentum P, and here's an angle theta measured from the horizontal. We did just a pretty simple SOHCAHTOA thing to say this is Px, which happens to be equal to P cosine theta. This is Py, which happens to be equal to P sine theta. All right? Hopefully you're not totally thrown by that, but if you are, like I said, I'll refer you to our previous video. So, yeah, I can write that. I can write that theta to P2 initial X component in terms of the whole momentum and the angle that it points at. Now this is P cis final X. This is M1 V1 initial. P2 initial is M2 V2 initial. And then keep the cosine theta 2 is P cis final X. Right? All we're doing here in these last couple of steps is, well, P is MV. P is MV. Yes? Okay? Well, I think we know all these things, don't we? M1, I'm going to just solve now. M1 is 40 kilograms. V1 initial 8 meters per second minus 60 kilograms times 7 meters per second times the cosine of 65 degrees. That is P cis final X. That gets me a P cis final X of 143 kilogram meters per second. What have we just found? We've just found the X component of the system's final momentum. So now we got to do a similar thing to find the Y component of the system's final momentum. All right, so I just gave myself a little more room. Let's do a conservation of momentum in the Y direction. All right, well, let's look at all the momenta in the Y direction. Well, guess what? Number 1 doesn't have F, right? This vector has 0 up and down component. So all we really get is negative P2 initial Y is, well, P cis final Y. And, well, let's see, this is negative P2 initial sine theta. Notice, here we're talking about the component. Which part? Well, the Y part. This is how we calculate or express the Y part. All right, so that is P cis final Y. Well, this is M2 V2 initial. Keep the sine theta. Well, this is M2 60 kilograms, V2 initial 8. Oh, 7 meters per second times the sine of 65 degrees. That's the cis final Y. Okay? I get P cis final Y part is 300, well, excuse me, negative 381 kilogram meter per So now we have the two parts of the system's final momentum. Let me do this and just expand a little bit here. Notice what I should probably make sure I do is be explicit about what this means, right? I might translate this a little. P sys final x 143 kilogram meter per second to the right. How do I know that? Because this is actually a positive answer. And if I also want to be explicit about this, we're really saying that P sys final y is, here's the magnitude of it, the size part, that away. How do I know that away? Because my answer was negative. So here's what I'm now equipped to do. I'm equipped to say, well, this system has these two parts of its momentum. So I can say there's a final momentum that has a part like this, 143 kilogram meter per second. It has a part like this, part like this, better, 380. I mean, is that to scale? Not really, but it's close. Kilogram meter per second. Again, there's no need to use a ruler and protractor here. That sketch is good enough. Which means that the net final momentum has that downward component, has this rightward component, and really the total final momentum is the resultant of those two vectors. It is this vector here, which I just didn't do a great job of drawing. It's this vector here, fine. So there is P sys final. Well, knowing what we know about the two components, do you think we can find the size of P system final? I do. I think we can probably say that P sys final, according to Pythagorean theorem, is P sys final, remove, final x squared plus P sys final y squared. Pythagorean theorem, because this is a right triangle. That's the point of doing some of this component stuff, oh boy, is making right triangles out of things that are easy to analyze using trigonometry and this here Pythagorean theorem. All right, so excuse me. So P sys final. Thank you. Thank you very much. Adios. So P sys final 143 381 P sys final is 407 kilogram meters per second. We're almost done, but that's not even what the question is. Remember, the question is, what's the velocity of the system afterwards? Well, we have the system's momentum. Oh, and here's the other thing. It's what's the velocity to include a speed and a direction. So we actually have a couple more things to do. I had to move to a new page here, but here's what we have now. We have, well, this is the system's final momentum, but we want the system's final velocity. So all we do here is say, well, P system final is M system V system final. So V system final is P this final over M system. Right? So that's 400, oh boy, that's 407 kilogram meters per second divided by, what's our system mass? Well, a 40 and a, oh no, nice, a 40 and a 60. Our system mass is 100 kilograms. Yeah? Okay. Now, this whole direction thing, well, guess what? If the system's final momentum goes in this direction, well, that means that the system's velocity is in that direction. Well, what direction is that? Well, here's one thing we can do. We can calculate that angle, theta. All right, and the way I'm going to do it is I'm going to say, well, here is P. So I'm just going to write, I'm tired of writing systems and finals. I'm just going to write this is Py. This part up here is Px. Right? So trigonometry says that the tangent of theta is Py over Px. Therefore, that theta is the inverse tangent of Py over Px. Or that theta is the inverse tangent of Py, 381 kilogram meter per second over 143 kilogram meter per second. And so therefore theta is 69 degrees. That angle that we've shown up here, 69 degrees. So our V-sys final, to be as complete as possible, I would say at 69 degrees below the horizontal. Okay? So, no small amount of work, that's for sure. All right? Like I said, we got some practice the other day, today or sometime, with, you know, how we do like up to this step and this step, and then what we did was use a ruler to actually measure how long things are. But that's not a typical way to do these problems. You typically won't have some nice to scale, there we go, some nice to scale drawing of vectors. You might just sketch them. So we have to calculate how big components are using expressions and trigonometry. Okay? And this one's a little bit harder because, you know, we have to write momenta in terms of m's and v's, right? And momenta in terms of m's and v's. And it can be tricky to know, wait, is, you know, there's a y subscript here but not here because we're, you know, expressing how big the y component is, or expressing how big the x component is. Notice there's an x here, but there's not an x here. There's how we find the x component. So those are the, you know, starting to get trickier parts. It's not tricky physics. It's tricky trigonometry, perhaps, and algebra, and keeping subscripts straight. So these aren't easy, but if you're methodical and with some practice, they become very doable. All right. So your job for the next time I see you is let's analyze this interaction. All right. Let's assume mass 2 is initially at rest. All right, and mass 2 moves off in that direction, and you've got to find the final velocity again, speed and direction of mass m1. And let's together, well, I'll just make assumptions for you. Let's say that m1 is 2.4 kilograms. Let's say that m2 is 4.0 kilograms. And let's say that this angle here, oh, V1 initial, what do you say? How about, let's just, how about a 15 meters per second? And let's define this angle here, theta to final. Let's call that angle, that looks like what? I don't know, 52 degrees? Sure, 52 degrees. Okay? So yeah, you find me how fast that other object, number one is moving after this interaction. All right? You're going to use a component method. and you're going to find, well, first find P1 final by finding P1 final x and P1 final y, right? You'll do your conservation in the x direction, you'll do your conservation in the y direction, all right? You'll get those two components, and then you'll use Pythagorean theorem to go back to here, some inverse trigonometry stuff to find the direction, the angle, theta 1 final. That says theta 1 final. All right? So when I see you next, that's what you'll have. Hang on a sec. Yeah, I just realized that we also need here V2 final, and let's call that, how about we call that, oh, I don't know, about 3.0 meters per second. All right, now, when you do this correctly, here's what your answer is going to be. You'll get, the answer is that V1 final is 12.6 meters per second. This angle being 18 degrees. So that's the answer. So see if you get there. Okay? Careful with sign. Careful with how you make, how you express your components of each of these two P1 final and P2 final. That's it. All right, folks. See you soon.